So what they did is they took the Muon g-2 experiment, which is a ring of magnets, and in a ring, the circumference is about 17 meters, 50 feet. And what they did is they took it, put it on a barge, brought it down the east coast of the U.S. around Florida, up the Mississippi River, all the way to near Fermilab, and then they put it on trucks, and at night they would shut down the highways, and they would drive this experiment to Fermilab, and they dropped it off, and that was, I don't know, 4 or 5 years ago or something like that. So what we did, the reason we did that is we could build a new magnet at Fermi, but we saved like 20 some odd $1 million. I don't remember the number. Saved a lot of $1 million building this thing. So what we did is we basically threw away all of the equipment, but we kept the magnet. We refurbished everything, put new equipment in it. We measured the magnetic field of this experiment to much better precision, and we started it working again. Now, how did it actually work? What we would do is we would shoot muons into this magnet, and if you take a magnet and you take a subatomic particle like a muon, which it's like a bar magnet, and if you put it in a magnetic field, it will precess like a top, just like, you spin a top and you see it go around. So what we do is we measure the speed at which the precession occurs. And the speed of precession is a mix of the strength of the magnet and the strength of the magnetic field surrounding it. So we measured the magnetic field of the g-2 at Fermilab to much better precision than was done at at Brookhaven. And now we're starting to get where we are. So we shoot the beam into the experiment. Now you want to make sure that you don't get the answer you expect. And so they even went so far as changing some of the parameters on the experiment and writing it down on a piece of paper, putting that piece of paper in a safe, and they did not tell the experimenters what some of the clocks were inside the experiment, so that they wouldn't keep looking at the clocks and saying, oh, did we get the right result or not? So they did all their measurements. It took a couple of years. And then they went to the safe from the guy who would not tell them anything, and they punched in the numbers. And what they found was that the measurement done at Fermilab agreed with the Brookhaven measurement pretty well. There was a slight disagreement. The Fermilab measurement has slightly larger uncertainties, but the Fermilab measurement also only analyzes 6% of the data. And so we have 16 times more data we've not even looked at yet. Oh. So now if you look at the Fermilab measurement and the Brookhaven measurement, they're kind of like this. They don't quite overlap, but they're very close to one another. So given that they're close to one another, we can say that the two experiments, in essence, agree. And we statistically combine the two measurements, and we now have one measurement that is the combination of the Brookhaven and Fermilab measurement and the prediction. And that is where we get about the 4 standard deviation difference. They disagree by 4 standard deviations. Now we're getting to the real interesting thing. If an experiment and a prediction disagree by 4 standard deviations and the experiment is right, then the prediction is wrong, and that means that the prediction, either there's just been a mistake or the prediction does not include correct physics. There's something missing. So that's what's very exciting, and that's what you saw in the press, is everybody saying, oh, the g-2 experiment discovers new physics. It hasn't really discovered it. What it's discovered is the standard model doesn't make the correct prediction, but it hasn't actually said what it is. And so that's what you saw in the press, and that's probably what many of your viewers and listeners know about. However, there's a however. The same day that the Muon g-2 experiment result was released, which was April 7th of 2021, the same day another paper was released, which was a new theoretical calculation of the magnetic strength of the muon. Now, the original calculation was very tricky because when you have this cloud surrounding the electron, you have to include what the photons do, what the electrons do, but you also have to include what the quarks do. And quarks are, anytime you do a calculation of quarks, it's very, very difficult. So the old prediction, what it did is it looked at old data, and it took the measurements from old data and included it into the calculation. So the theoretical calculation was a combination of math and a little bit of experimental input. However, on April 7th, a new prediction was done, which is called lattice QCD. So this is a case where it's you take quantum chromodynamics, which is the theory of the strong force, you set up a 3-dimensional grid, and you use petaflops of computer power. Think about that. Petaflops, not gigaflops, not teraflops.
Wow.
Petaflops
A lot of power.
of computing power to calculate what's going on between these grid points. And so they did a calculation of the G factor for the muon. And what they found is their prediction agrees a lot more with the experiment. So if the lattice QCD measurement is true, then, or not measurement, the lattice QCD calculation is true, then maybe there's no disagreement at all. It could be that the standard model agrees very, very well with the measurement. However, you know, there's always a however. This is science.
Let's hear it.
There's about
more,
like
however.
6 more
I
however.
like it. No, I love it.
Yeah. So the thing is, with the lattice QCD measurement, you have to ask where their uncertainty came from. And their uncertainty came from the researchers' uncertainty in their method. So they had to do things. I mean, lattice QCD calculations are really tough. I mean, they've been around for a while. They can do things like predict the mass of subatomic particles with some precision. Nonetheless, they had to make some decisions, and when you make decisions, you assign an uncertainty, and their uncertainty was a systematic uncertainty. So it may be that they made a mistake, and they acknowledge that. So now where are we? Well, we have a prediction using data input, we have an experiment, and we have a prediction using lattice QCD. The old experimental input prediction and the data disagree. The lattice QCD agrees pretty well with the experiment, not perfectly, and kind of disagrees with the experimental prediction. But the lattice QCD measurement has concerns in how one handles it. Did they do it right? So there are at least 6 other groups of very good physicists. Mind you, the physicists who did the lattice QCD prediction are fantastic. They're the best. But that doesn't mean that they're right. It just means that they're very good. But there are 6 other groups who are similarly good, and within a year, they will be able to reproduce the lattice QCD measurement and see, or prediction rather, and see if they did it right or not. So that's number one. In addition, on a time scale of about a year, the g-2 experiment will have taken 16 times more data, 16 times more data than they've taken so far, and they will make a better measurement. And so on a time scale of about a year or so, what we will know is if the lattice QCD prediction stands up. If it does, then maybe there's not it's not as interesting as everybody thought it was. The standard model agrees with data. However, if we find that the lattice QCD prediction is somehow incorrect, then we're back to where we are, where actually the disagreement between the prediction and the theory has even grown. Now, so we have a case of where there's no problem at all because they just did the prediction wrong in the old days, or it's right and there is a problem. Now we get to the last question. What could it be? And that's a tougher question. And it's a tougher question because new possible physics that could explain this, it's not completely well defined. There is the possibility that we have some new physics that the particles that generate new particles that we don't know about that interact with muons but not electrons. They are low mass particles who interact a very small amount of the time. Or, alternatively, they can be high mass particles that interact a lot. But because they are high mass particles, even though the interaction is very high, it's hard to make high mass particles because of Heisenberg uncertainty. High mass particle is high energy. It's just difficult to do. And so you say, well, that's weird. How come we don't know that? Well, it's kind of like someone, if an experimentalist measured density and you were asking, well, how big is something and what's its mass? Well, if you know the density, it could be a small object with a small mass, or it could be a big object with a big mass. The density measurement doesn't actually answer your question. But what you do know is not a small object with a big mass, because that would disagree with the density. So that's where we are. We have a measurement which allows for either small mass unknown particles that interact rarely, or large mass particles, unknown particles, that interact a lot. And so now you know everything I know about this, and what you need to really do is ask somebody in a year, what's the answer? Because I don't know the answer. Mm-hmm. Nobody knows the answer.
Nobody.
That's the deal. So, okay, that was a lot of information. But
that was good information, though. Now we know. Now we know the options that we have. You know.
Yeah. And quick question: why didn't they use, for example, like the tauon? Like, why isn't it the tauon g-2?
Because, okay, so electron lives forever. The muon lives for 2.2 microseconds, so 2 millionths of a second. The tauon lives for about 10 to the minus 12 seconds, so it lives a millionth as long as the tau, or the muon. So it would be a sensible thing. It's a fantastic idea, but you would have to somehow accelerate the particles to such energies that the Lorentz gamma would allow them to live much, much longer. And that's just not feasible. In addition, making taus is hard. So it was a balance. You could make more muons, and they live for the right amount of time. So what you said is a fantastic idea, but from a practical point of view, impossible.
Right.